Hello and welcome to the lecture series on applied thermodynamics. We are considering reciprocating air compressor for our discussion. In today's lecture, we are going to look at a derivation for the work done by the compressor without clearance volume. To begin with, let us be clear about the type of compressor we are analyzing. Looking at the classification, we are considering positive displacement type of compressor, and under that we are focusing on single acting reciprocating air compressor. A compressor is basically a machine which is used to compress the working fluid, which may be either air or a gas, to a very high pressure, and it is delivered at the delivery end in order to meet some specific purpose. One of the classic example for the application of air compressor is spray painting application, and it is also used for some pneumatic tools, powering, etc. Schematically it is represented as shown here. So we have a prime mover, basically a motor powered by electrical energy, and it is in turn powers the air compressor. It is very clear that the area is reducing in cross section, which typically shows that as the volume is decreasing, there is a rise in the pressure. Now looking at the action that is taking place within the compressor, we can see from this that the reciprocating action helps in increasing the pressure of the air. For our derivation, we are considering a PV diagram without any clearance volume. So there is no any clearance volume. Now let us look at the PV diagram, and it is very clear that there is no any clearance volume shown here, and the swept volume starts from C to 1 as shown here. And we know that the area enclosed by the PV diagram indicates the work input to the system. Therefore, in order to compute this work, let us analyze this, segmenting this into different areas, and we have a summary of this. The area within the curve is given by a segmental area as shown here, and then we have the area of 0 to B, B to 2, 2 to D, and 0. This is a rectangular area given by P2 into V2, followed by the next segmental area, and this is a polytropic compression, and the equation is well known to us since it is derived in the basic thermodynamic class, and it is given as P2 V2 minus P1 V1 by n minus 1, and the last one is another rectangular area given by length into breadth, that is P1 into V1. Just by subtracting the base segment, we can get the area enclosed within the curve, and that is a logic we are going to follow. By substituting these equations, we get the equation of this form, and further taking the LCM, we get a simplified version of the equation, and then getting rid of the like terms, we cancel P2 V2 and then P1 V1, and then we have the final form of the equation as shown here. Further, one can replace this P2 V2 P1 V1 in terms of ideal gas equation, and expressing that in terms of characteristic gas constant R. And now expressing the same equation in terms of pressure ratio, we are going to replace T2 with P2 by P1 using these property relations, and we are going to now replace T2 with pressure ratio, and the equation gets reduced of this form. Further, translating the same equation for the isentropic equation, we get n has to be replaced by gamma, and then we get the final form of the equation of this kind. Therefore, these are the different forms of work done equations expressed in different property variables. So this can be used while solving the problems. We recommend the following books to understand more the subject, and we thank you for your attention, and in case of any queries, please feel free to contact us on the following email. Thank you for your attention.